always interested into like math and data structures and stuff. And today we're gonna talk about the future of Ethereum, like what is going to happen. And this is the Ethereum roadmap. Maybe some of you have seen it. Actually here, maybe just a quick check. How many of you are actually coming from like Web 2, not like Web 3 people, but like Web 2 people that, okay, so I think most people here are kind of part of the Web 3. So it's not, yeah, somebody that sees that for the first time. But yeah, for the Web 2 people, so this is a diagram that shows basically the roadmap of Ethereum. So what is going to happen in the future, and it's split into a couple of stages. And one of them, which is the one that we're gonna talk today, is called the Verge. And this is the part about implementing some new data structures, about how the state of Ethereum is going to be kept. And this is about making the Ethereum stateless. And we're gonna see what actually this means. So what is the current problem? When you sync a new Ethereum node, it's gonna take a lot of time. A few days, maybe a week. All the state that you need to download and process right now is around 2 terabytes, and it's increasing. So you can't actually run a node on your mobile phone, even if it's a Solana phone. No, not gonna work. Also, you basically, because of this, you basically need to use a centralized RPC provider. So you need to rely on somebody else to tell you what is going on right now at Ethereum, like how much I need to pay to buy ETH from Uniswap, for example. Like you need to rely on a centralized third party. And we actually, yesterday, there was a panel about infrastructure and dev tooling. And there were people on stage that their business is basically running nodes. And they were explaining that it's getting harder and harder to run these nodes. And there is actually this example that on Binance Smart Chain right now, it's impossible to sync a new node from the very beginning. There is no big enough hardware in the world that is going to allow you to do that. Now, for Ethereum, that's not the case. You can like run a full node and it's going to take a few days. But yeah, like for Solana also, that's very problematic. And another thing that is also the kind of a status quo right now is the bridges. Bridges right now, they rely on message passing. And in order to pass these messages, you need to rely on somebody, like maybe not like a centralized entity, but maybe like a set of validators, like a separate set of validators that, no, it's just additional security assumptions. So that's not ideal. And we actually see what happens sometimes, with wormhole hack and with multi-chain problem now, where, we can't find the CEO, so money are stuck. Sorry, guys. So let's dive into a little bit of technical detail. So the current state is the following. So everything on Ethereum, like the database of Ethereum, is kept in a so-called Merkle tree. And a Merkle tree, here it's like a simplified version of it. You can imagine it's like a tree, and all the data is at the leaves. This is like where everything is kept. So you can imagine this is just a key value store. So we have like keys and we have values. All the values are at the leaves. And then for each leaf, we compute a hash. And then for for every siblings of each node, we compute the hash of the 2 hashes, or like the other hashes. And now we do hashing, and we end up with a single hash. And this is the root of the Merkle tree. And this is basically the fingerprint about the current database of Ethereum. Like if the fingerprints match of what we computed and what somebody else is telling us, we know that, yes, he's telling the truth, because we can validate that. So this is how it basically works. And here we're gonna just review, like, the blockchain is basically this thing that you have a state X, which has a given state root, which in this case, it's like 0x beef. We have a bunch of transactions that are in a block. These transactions execute on state X, and you get state X plus 1, so the next state. This is what's called a state transition. So you take state X, you execute the transactions, you get the new state. And it has a new state root. And this is like 0x dead in this example. So you should be able to execute these transitions. And this is how your state evolves. Now, the Merkle trees, they allow you to generate this thing called a witness. So when you see witness basically in the blockchain or the cryptography literature, what this actually means is that it's just some bytes that you can use to validate that given data is indeed in this tree. And you can do this in a kind of a quick way. So you don't need to keep the whole database somewhere. Because if you have the whole database and somebody tells you, yeah, this key, the value is that, you can check that. It's easy. So we have all the 2 terabytes. But if you have a witness, then you don't need all the data. Only using the witness, you can validate, yes, indeed, this data is inside the tree. So Merkle trees, they allow you to generate such kind of witness. And the way this works is like this. So if we have this data, which is like D3 here, which is like the data that we want to validate that it is in the tree. Oops. So we want to validate that D3 is indeed in our current state. So what we need to do is we need to just have a list of a bunch of hashes that are along the path to the root. And when we collect these hashes, we will be able to validate that indeed the root hash matches. And if this D3 is something else, then we won't be able to do that. Like it will be impossible to generate such kind of a witness. So this is what basically a witness is. Now with Merkle trees, what happens is that the wider this tree is, so the more siblings you have, the bigger this witness becomes. And that's a kind of a problem. Right now, the Merkle tree in Ethereum is like, I don't know, it's quite wide, maybe like 10 or 15, something like that. I don't remember the exact number. So what happens is that generating these witnesses for Merkle trees, they're actually quite large. So it's about 3 kilobytes per witness. So, and where I'm going here, like the idea is that, well, can we somehow do this state transition without having all the 2 terabytes on our hard drive? So to be able to make sure that, yeah, indeed, these transactions lead to this new state root, but without downloading all the data. So potentially we can try to use witnesses for this. But in order to generate witnesses for all the data used in a block right now, for the Merkle tree, that's going to be 18 megabytes. And there is a new block every 12 seconds. So if we actually implement this, then we need to transfer 18 megabytes every block around all the nodes on the network. So basically, we're going to DDoS the whole network. They're just not going to work. So basically, if you want to do this stateless Ethereum right now, there are ways to do it. Like, technically, it's possible. But in practice, it's not, because it's just too much data for these witnesses. And given that, this, the state is growing and all this, like, yeah, I mean, it's just not going to happen. Another thing that also complicates the whole thing is that when you have reorgs, you need to keep even more data, because you need to be able to unwind the previous transactions, and yeah, that complicates things even more. So, but theoretically, if we have this approach where we have these witnesses, we will be able to have these state transitions without keeping all the data. And now, let's look at what a Merkle tree is, which is basically a data structure that has these properties that we need, and it's actually gonna make it work. So you can imagine the Merkle tree is pretty much like a Merkle tree. It also allows you to hash this data, although the hashing is done in another way. And this another way is, we're not going to actually explain how it works because it's, your head might explode. But basically, it's not hashing. It's not like a SHA hash, but it's something called polynomial vector commitment, which is some moon math that relies on elliptic curves and all that kind of stuff. But the properties that it has is that the witness now becomes like 200 bytes instead of 3 kilobytes. So it's like orders of magnitude better than using a Merkle tree. So we can estimate that currently if a block is 15 million gas and we have 2,500 gas per access to the state, we have around 6,000 accesses to the state. So that's the amount of witnesses in the worst case that we might need. So that reduces the total witness size to generate for a block to about 1 kilobyte. And 1 kilobyte is great. Like we can transfer this amount of data every 12 seconds. Now, where is the trade-off? There's always a trade-off. Like there is no free lunch in software engineering. So the trade-off is that it just takes more time to compute this Merkle tree, to update it. But we can see here that it's actually acceptable. So if we go into a little bit like technical details, if right now, you can see for Merkle trees, it takes like, and for Ethereum, this is the K-Airy Merkle tree. It takes like ON to construct and K log N to update, and this is the proof size. For Merkle tree, we increase linearly the amount of time it takes to construct, but we have also like order of magnitude smaller proofs, and that's like an acceptable trade-off. So it's harder, it takes more time to update it, but given that computation scales better than bandwidth, that's an unacceptable trade-off. So if we look at the structure of a Merkle tree, it's pretty much the same like with the Merkle tree. Like we're not going to go into the details of how exactly it works because it's like connected with a lot of like polynomials and stuff. But basically, we have the data in the leaves, and then we generate these polynomial vector commitments, as we go up. Cool. So how a stateless block is going to look like in this case? So let's say that we transition, we transition from Merkle trees to Merkle trees, and now we want to have stateless Ethereum. So what is going to happen is that every block is going to contain a list of transactions, and then together with the list of transactions, it's also going to include all the data that this block needs in order to run as a key value store. So we put just, because when the validator creates the block, he executes it, so he knows what data this block uses. So he can make a list and say like, okay, this is the keys and values that will be needed for this block. It's going to be included there. And also he's going to include a list of witnesses. And what this is going to allow is that if I'm a node operator and I download the block, I see the list of transactions, I need all the data that I need to execute it. And now I also have the witnesses, and I can make sure that this data is actually correct. So I don't need to keep all the 2 terabytes on my machine in order to validate it. And this is basically going to allow to run Ethereum node on your mobile phone, basically. So what are like the benefits? Like the clear benefit is that you don't need to keep like 2 terabytes hanging around. You don't need like a fast SSD to sync the latest, the tip of the chain. You basically need only the blocks, so you don't need to download anything else. Everyone can run a full node now. You don't need to rely on a third-party RPCs in order to validate the data. Now, you're going to need the RPCs for another purpose, and that is if you want to actually create transactions. If you want to, let's say, you want to execute a swap on Uniswap, you need to know what is the current liquidity in order to make sure that the price is correct. So you're going to ask an RPC node that actually has this data in place to tell you like, okay, tell me what is the current price of Ethereum on Uniswap. And this RPC node is going to reply to you. But it's also going to reply to you with a witness. So now you can make sure that the RPC is not lying to you. Because right now, if you rely on a centralized RPC provider, he's going to serve you whatever data he wants. And actually, that could be a security issue, because if the RPC provider lied to you about the current liquidity on Uniswap, then you're going to sign a transaction that is going to be unfavorable for you. So it's very easy for an RPC node to lie to you that Ethereum is like $5,000 right now, and you're going to be, okay, I'm going to buy at this price. And then you submit the transaction, and you're going to be like sandwiched, and MV bots are just going to destroy you. So if you have witnesses, then the RPC providers will be able to provide you an additional cryptographic proof that, like, okay, this is the witness for the data that I'm giving you, and now you can also validate it, like on your mobile phone without any additional stuff. You only knowing the root of the tree, that it's not actually lying to you. So in this new world, we're going to have like two types of nodes. We're going to have like full nodes that are having all the data, and we have the stateless light nodes that run like everywhere. And light nodes are going to ask the full nodes, like, okay, give me just some of the data that I need right now. These nodes are going to serve it together with the witnesses, and you'll be able to validate it, and it's going to be great. Another big benefit of transitioning to this new data structure is also that it's much easier to put it in a snark. So this is like a zero knowledge like box that allows you to generate also a proof that a given computation has been carried on. So it's not only about a proof that we have certain data, but also that a given computation has been done. And that's valuable basically to make sure that we might transition actually in a world where you even don't run the Ethereum transactions at all. You just receive ZK proofs that the computation for these transactions has been carried on. And then using this proof, you don't need to run the transactions. You just verify the ZK proof. And then it becomes even more lightweight. You basically don't run the EVM code at all. So Verkle trees are much more snark-friendly compared to Merkle trees. And that's because snarks, they don't like SHA hashes. I think yesterday somebody told me that right now, to generate a proof for a single SHA hash, it takes like 1 minute, which is insane. Like, if you need to generate a proof for like the whole consensus of Ethereum, it's like billions and billions of SHA hashes. So that's going to be too complicated, too much time. And now, okay, we saw what is the benefit for basically the users and like node operators. Like, we're going to make validation so much easier. We can easily run nodes. But what about the bridges? Like, this is something that we haven't talked about. And it's kind of hard to figure out, okay, what is the connection with bridges here? So let's just do a little bit of overview how the bridges work. And we actually did that in the beginning. So they pass messages. But in order to pass these messages, they need to facilitate some network of validators, like on top of the Ethereum consensus. Usually, these validators are not as decentralized as the Ethereum validators. So that's a kind of a problem. And these are basically like very centralization points. And actually, Vitalik did a blog post about like what he believes is the future, and he was explaining that having a multi-layer 1 future is problematic exactly because of bridges, because they become this weak point. And if you manage to break the bridge, you pretty much is able to wreck the whole blockchain. And this is actually something that happened with Phantom like a week ago. Like the multi-chain bridge got exploited, and people went crazy about Phantom. So the question is, can we utilize the same technology to improve bridges, and how we can actually do that? So the way we do this is actually very simple. So imagine that you have 2 blockchains, and the state of this blockchain is Verkleized. So they use these Verkle trees to keep their data. So now what you can do is you can take the state root of one of the blockchains and submit it to another. Only the state root. So that would be equivalent to taking like the current Merkle hash or whatever. As we said, it's the same. You put it on the other blockchain. And now imagine you want to execute a transaction on one of the blockchains that needs some data from the other. which is the standard bridging problem. You need to know, you're on Arbitrum and you want to know, okay, does this address own an ape on Ethereum, let's say? And you need to run a smart contract that does something. So if this address has an ape, then, I don't know, I'm gonna airdrop him some shitcoins, let's say. So you have the state root of Ethereum on Arbitrum. And when you execute the smart contract, what you're gonna do is you're gonna pass the data that you need to validate, plus the proof, the witness that we said, like the same witness that can be used for the other thing. And now the smart contract, what it can do is, okay, given that this is the current root on Ethereum right now, this is the data I want to validate, this is the witness, validate the whole thing into the smart contract. And if it passes the validation, that I know, in this moment, I know, yes, indeed, at this state root, this data is present on Ethereum. So now I can continue executing and I can do like the airdrop or whatever I need. So in this case, you basically, by only submitting the state root of Ethereum on another blockchain, you pretty much bridge the whole state of Ethereum. So now every smart contract on this other blockchain can validate all the data on Ethereum just by having a witness. And when you think about it, in order to do that, you kind of don't need this additional security assumptions about like a network of validators or anything like this. The only weak point in this whole story, when you think about it, is how do you make sure that when you update the latest state root, it's actually correct? Because if you actually want to attack this system, then I can just craft a state root in which I'm the owner of all the Bored Apes in the world, and I submit it to the other blockchain, and suddenly, it's like another reality. So in order to fix that, we pretty much need to rely on zero knowledge. So if we are able to validate the consensus that this state root is correct using a ZK snark, this is what we talked a bit earlier, that if we are able to generate a snark that this list of transactions indeed reach this new state, then once we submit the new root on this blockchain, we can also submit the proof, the ZK proof, and the contract that accepts the root, it can validate that, well, this root is actually correct. Now, if we don't have this ZK thing, then we indeed need to kind of rely on this validators network. But you can argue that it's not like much better than what we have right now. But the truth is that actually you can monitor what is being updated on the blockchain, and it's kind of very easy to see if somebody submits an invalid root. So yeah, I mean it's kind of much easier to monitor, I would say. But the moment when we manage to snarkify the consensus, which is also something that's going to happen in the future, we basically going to reach this ultimate decentralization where we don't rely on like any additional validators or anything. We rely solely on cryptography in order to pass state around different blockchains and validate the blocks. So that's basically how you can use these Verco trees to improve the things. Here I listed some resources which you can take a look at if you're interested in. So there are two projects that I know about that are working on this kind of a bridging thing using such kind of witnesses. One is Lagrange and the other is Herodotus. And it's very similar, although like they have like slight difference in their approach. But I would recommend to take a look into that, especially if you have a problem where, okay, I want to maybe deploy an app on a layer 2, but this app somehow needs to rely on some state on Ethereum. So bridges could also be expensive, like you need to pay for these messages to go around. So we can actually use the technology that these companies are providing to basically utilize this. And it could be, we know that all the NFT trading happens on OpenSea on Ethereum, but if we want to build like a game, it needs to be on like layer 2 or layer 3 and whatever. So that's going to be a bigger and bigger problem as we go. The other resource is this guy, I think Italian guy, he actually wrote an Aragon version where the state is completely Vercoized, so using Verco trees instead of Merkle trees. And he has even like a testnet for it, and you can actually take a look into it. The other one, which is like a PDF, is pretty much the first implementation of and test of Verco trees that was done by a research in MIT. And this is, if you look at the URL, this is research from 2018. So we are talking about cryptography that is pretty much like 5 years old. Well, that's not the cryptography, it's like the data structure, because the witnesses in the cryptography think it's probably older. So you can take a look into that. It shows some statistics and stuff. And the other two are one EIP from Vitalik that explains how the transition actually is going to happen, because that's actually not trivial. Like you need to transition from Merkle to Verco trees, like migrating the whole 2 terabytes to another data structure. It's going to be a challenge. And also there is a blog post on ethereum.org about Verco trees. You can also read that for more details. So that's pretty much it, like as an overview. I'll be happy to take any questions if you have, and I hope you took something from this talk. Yeah.
Hi.
Hey.
Actually, what first comes to mind is usually when you work around cryptography, it's sometimes tricky in terms of you might have all components of your cryptography and new data structure, which is it's pretty much like B3, but instead of min-max, we use some polynomial, as I can see. So actually, in general, reduction, like tree size like this is just prolonging the problem, but whatever. It's like K could be really huge. But what I'm really concerned, because from the top of my mind, I can figure out why this has the same security level as Merkle tree. Because in Merkle tree, you have each part on the line, and you basically again go to the root and check everything. That's all you carry, and you can sort of even cache parts which you use frequently, which would be to the right because it's like in history more new. Maybe not, it's just statistical. But here it will involve, well, it's really hard to formulate my question because it just come to mind right now. But in general, do you have any idea about researchers? Is it more secure, less, or it's the same?
I would say it's maybe the same. The concern that people have is that both, I believe, Merkle trees and these Verco trees, they're not quantum resistant. So the next level of security that we're gonna talk like in the future after all this is done will be how to actually make all the cryptography quantum resistant. I see this as a kind of a recurring topic that people are talking about. But the thing is, like, there's these problems that we have right now that needs to be solved. So it's much better to use this like cryptography to fix them, although we know it's not quantum resistant. And then start thinking about, okay, how we bulletproof our cryptography. Because quantum resistance is actually a problem that's going to be so wide and so big that pretty much everyone will be trying to figure it out. Like, it's not impacting only blockchain, it impacts like HTTPS, like SSL, and like all these other protocols. So, I mean, in that sense, it's pretty much the same security level. You can measure the security level also in another way, which is how many bits of security this given scheme has. And I believe that with these Verco trees, the level of security that, and it's the Verco trees plus like the elliptic curve on which they do like what is like the field the computations are done. I think it's 128 bits of security, basically. This is the amount of.
The main concern, if you use polynomial instead of just plus minus, which you use in Merkle tree, like simplifying. So usually it's like when you measure something, you can increase your mistake by using polynomials, especially if you multiply and divide. And it seems like in polynomial, as I saw from formula, it could be the case, maybe not, it's not clear, but whatever, it's just what comes to mind, so it's like, maybe it's not a concern. Maybe
So
people already solved that.
I mean, you mean that polynomial seems like kind of easy to manipulate in some way? Yeah. So you need to take a look at the moon math, basically. But it's just amazing. Like it's actually like they do all these type of tricks. So I think the founder of Starkware kind of tried to summarize it in easier terms, which was like in the world of polynomials, it's very hard to lie, because if you lie, and we are talking about polynomials that are like big polynomials going through like a lot of points, if you lie for one thing, the whole thing just, because you can imagine it is, you kind of interpolate a polynomial that goes through a lot of points, and then you need to like commit to a certain value. So if you kind of try to lie in this setup, the polynomial is just going to be completely different. It's going to change like completely. So it's just not possible to lie even once in this kind of scheme. So I mean, if you look at the math, it totally makes sense. So. Mm-hmm.
Who is first?
Okay, that's it. Okay, just a quick understanding question, right? So you said, let's say I run my node on my phone, right?
Mm-hmm.
The witness I'm getting only tells me like if the data I'm getting is correct, right? So
yes.
if I want to verify the transaction, I still have to pull the data from somewhere, and like the only thing the witness gives me, assuming I trust the witness, that I know, okay, is this data correct, right?
So in the block, you're gonna have both the data that you need and a witness that the data is correct. So if you want to execute the transaction is gonna use like keys A, B, C. You're gonna have like A, B, C, this is the values that these keys have, and then a witness for each one of them that they're correct.
Okay, but the block is bigger than 200 bytes, right? I would still have to pull a lot of data on my phone, do the verification, but I don't have to save it, right?
Yes. So you're probably gonna save the block like with the data. Although if you validated the block, you probably don't need the data, to be honest. Like once it's validated, you can probably throw out the data and even the witness, I guess, because I don't see why you would need to keep this around. You just need the state root, and that's it. So yes, indeed, the blocks are going to become bigger, but when you compute like the size, it's completely okay to transfer this every 12 seconds.
Okay, so it's more like I'm not concerned about the witness. I'm more concerned about the data I need to pull in my phone to do the verification, right? It's more kind of a storage versus bandwidth trade-off.
Yeah.
Okay, thanks.
Hi, thanks for the presentation. I'm curious, what is your thought on how far are we from ultimate decentralization that you mentioned? And do we need some more changes on the consensus layer to achieve that?
That's a good question. I would assume that we are pretty far, unfortunately. I would say at least maybe a few years until we reach that. So I can't say like estimated ETA when we're gonna reach that and all this. But yeah, I mean, we can see that there is so much research around ZK EVMs and that kind of stuff. So that's very promising. But until we reach this, like, there are proof of concepts out there. Like there is this blockchain called Mina, I think, that is completely snarkified. So it's not something that we are kind of just inventing. There are people playing with this concept. Yeah, I would assume that first we need to transition to Verco trees. Then it's going to be certain time. When you look at the EAP for the transition, there will be certain time where we run with both the Merkle tree and the Verco tree. Like they're going to be both present in the client, and the data is going to be migrated slowly. And then we need to figure out how to drop the Merkle tree like completely from the client node. So that's going to be another kind of fork, I guess, or something. So once we reach that, then I guess it's going to become like within reach to also snarkify the consensus. But it's nice that we have these projects that are kind of playing with this idea, like Lagrange and Herodotus. It's great that they kind of playing with this concept, and yeah, maybe they kind of push this initiative further. So we'll see. Other questions?
Thank you for the presentation. So actually, I think you mentioned Mina. I think what they are trying to do is do the recursive snack and to, I mean, shrink the Bitcoin's verification into several kilobytes or something. And I think there are a lot of techniques to do how to make the whole Merkle tree or how to make the whole blockchain to be verifiable and much more smaller. So why we call it stateless? I mean, a lot of blockchains, they are trying to do the similar ideas with different techniques. What is the difference from the stateless Ethereums and others? Yeah.
So there is certain security assumptions, with this Mina that, basically so the nice thing about snarks is that you can recursively kind of merge them together. So if you generate a snark proof for a bunch of transactions, then it's very easy to merge them together and get a snark for all of them. And this is very easy to parallelize. So that's amazing. But one of the security assumptions of Mina and kind of could be problematic is this long range attacks, which I won't kind of fall into details because I actually need to refresh my memory about it. But it's there are certain assumptions if you want to fully kind of snarkify the consensus and don't have any transactions going on, like it's kind of a hidden and all this. So yeah, like unfortunately, I'm not super deep into the Mina blockchain, so I can't kind of elaborate on this. But yeah, it's an interesting thing to research. So sorry, I guess I can't help that much giving you concrete details. But check long-range attacks and weak subjectivity, basically. These are the two types of kind of things that could be problematic. And I think we're kind of running out of time. So yeah, thank you very much. I hope you're not asleep at this point. So.